So in English,
yeah. Yeah, so good afternoon, everyone, and thank you very much for joining us. Today, we are extremely happy and pleased because Professor Claudio Faccenna has accepted to give us a talk on a topic which I must admit is extremely challenging. It's all about the dynamics and geodynamics in the Mediterranean. Professor Faccenna has half a position in GFZ Posdam and the University of Roma. So, Claudio, the floor is yours.
Thank you very much, Catherine, for a very nice invitation. Very happy to be here. I would be more happy to be in Kigali. Actually, I was saying that I've been there for more than 30 years ago, it was one of my best moments in my life because I was the eruption of Nyiragongo, so also was visiting that, and the countryside was beautiful, and so I really enjoyed that. So today I'm in charge to show you some of the progress we've been doing on trying to understanding the functioning of the Mediterranean. And this is I would say, as a collaborative effort between numbers of people and friends and colleagues that are doing this work with me during the years. So it's like, for example, Thorsten Becker from UT Austin, but there are also people from France, Laurent Jolivet and Jean-Pierre, which is not anymore with us, people from Italy, Roma 3, and then Vicky Royden from MIT, Fabio Capitanio from Monash, and then Claudia Piromallo from ENGV, and many other people that I'm not mentioning here, and all the students that also participate to this effort during this year. So let me first introduce you to the problem of the Mediterranean. So is this considered like a tectonic puzzle? Because it is the boundary between two large plates. This is Eurasia on one side and Africa on the other side, is accommodated by extremely narrow. Another thing, if something wrong, please raise your hand. I can see that from here. I can interrupt anytime. I'll be happy to answer. So solve any question or issue that if I'm not clear or something not clear, please raise your hand on the Zoom. It's possible and invisible for me. So the boundary between Africa and Asia is markedly Mediterranean, but very narrow plate boundary, diffuse over an area that going from the Alps to North Africa and do a very shaky and narrow belt like around the Berics, the arcs like in Calabria, then the Alps, the arc of the Carpathian, the Mediterranean Hellenic. We'll see these things of the arcs, it will come back with that. And also, interestingly, it's considered a puzzle because there are microplates, at least from a geodetic point of view, that are really moving, and we will see independently, irrespective of the overall convergence between Africa and Eurasia. And between these, I mean, worth mentioning Adria plate, squeezed between three orogenic belts, the Alps, the Apennine, and the Dinarite. Anatolia, Turkey, that is moving in this direction, and Aegean in this direction. Right? So today, I'm trying to do with you a revision of the tectonic, geodetic, seismic data, and then go into model. And I would like to demonstrate you that the complexity we see on the surface is actually maybe well explained by a relatively simple pattern of mantle convection and subduction. So it's a diffuse plate boundary. It's very complicated, but at the end, it may be not too complicated as it seems to be on the surface when you look at the things from below. Let me frame the problem in general terms. Africa is moving progressively in time to Eurasia, so opening the South Atlantic is counterclockwise. This is something that we know. And then you can see also India departing here and detaching from Africa at the moment. So the velocity of convergence relative to Asia is this red little stick here that show that in 60 million years, more or less. This is every point, it's like 5 million years. You have the motion of a point that is now in northern Tunisia. It should have been something like that. And you realize immediately that the motion is more or less north-south in the center of the Mediterranean, and then turning to more northeast, northwest as it is now. And the motion is pretty slow because Africa is a slow plate. It's moving very slowly with respect to many other plates that move at very higher convergence in the order of average centimeter per year. So Wiki Reuden and I start thinking about the Mediterranean in time, and with their fantastic graphic touch, they can show the evolution of the Mediterranean in the last 25 or 30 million years. This is the moment where the Mediterranean really make a big revolution. So it's an important moment from 30 years more onward. So at that time, the paleogeography was like that. This is the white Africa. This is these two blue plots. So it's oceanic lithosphere, and in the middle you have some continental blocks. Okay, so there was active. Two subduction was active. One is running here in the Atlantic Trench. Another one in the Western Mediterranean, near this trace of what is part of Italy, Sardinia, and Corsica, France. And then you have reversal of the subduction with the Alps that were consuming the little basin here. So the dark blue is deep ocean, the light blue is a continental platform, and the white is emergent continent. So you realize that these two little ocean, that is the last pieces of ocean of all the Tethys that is left over, and then they are ready to subduct. So let me follow in time what happened during 20. You see that the evolution is that the trench was consuming this light blue material, so continental, but and this one start retreating back, so rolling back. What we say is that the trench is migrated, the subduction is migrated backward, retreating. We can see that, and then consuming all the material. The velocity of Africa is low. This subduction zone go fast. We are 15 years, so a million years old. Alps are dead already, so no more active, only in southern and southern Alps. And these two trench, while they are retreating, they form the arcs, and they're progressively digesting this material, and it's breaking off in northern Africa here. And then this trench start retreating again, and then is arcuating, and is arriving to the present day setting. So you can see that when starting from here, then to here, you are consuming all the Adria plate, a large part of the Adria. So this is what is left over. And then we still have to consume this blue ocean very old. And while you're doing that, you also realize that we are opening some basin on the back arc basin. Okay, first the Ligure-Provençal and then the Trinidad. Okay, we can also play a game, stretch our mind, and think, so what will be the future of the Mediterranean? And so we imagine that the future will be probably that this subduction zone will try to consume also this leftover parts of the ocean, joining the Calabria, so in simplification, and maybe opening a basin, and then we can arrive up to 10, and then our fantasy is probably not enough to imagine what could be the future. But coming back to data, we can see that how this reconstruction done by evidence from the field can match what we can see from seismic tomography, for example. And here, Claudio Piromallo have been done a great work on coupling together regional teleseismic wave on zooming in this region. This is a P-wave model with slices and kilometers here, and you can see high velocity zone that correspond to the root of the Alps, or the Apennine of Sicily, and also the Dinaride, the Hellenites. And then when you go deeper into the mantle, this high velocity zone is getting larger. And then when you arrive to 660, to the discontinuity in the upper lower mantle, then it's an enormous amount of material blue. So this means that the high velocity corresponds to probably temperature, cold temperature, where the seismic ray goes faster with respect to a model. And therefore, we can interpret that as a subducted material. That means that there was an ocean between Africa and Eurasia, called the Othetian Ocean, that now is at 600 kilometers depth, completely down. So it was completely subducted, and now it's flooring the upper lower mantle discontinuity, stagnating on the 660 discontinuity. Well, that was interesting, actually. We can also see another set of data that are also very important for our story, is that is the anisotropy. You know, when the seismic ray arrived, polarized along fast velocity, that gave us an idea on the horizontal component of direction of the mantle flow. And this is, well, we have a lot of data on that kind of stuff, and we see that most of them are east-west in Spain, also north-west southeast in the Eastern Mediterranean. And when you go along the subduction zone, things is getting more complicated. But it's doing swinging here around the Alps and going east-west also. Okay, so most of this anisotropy is pointing out against the active subduction zone, which is the Calabria and the seismicity is clear. There's a lot of earthquake. It's getting more intense crustal earthquake while moving toward the east, because here the velocity of convergence is higher. And the focal mechanisms tell us that most of the seismicity is on compression because there are convergence. But there are areas, especially in the Apennines, for example, or in the internal side of the Hellenites, where there is extension. And when you go in Anatolia, we know that there are strike slip faults that are accommodating the eastward motion of Anatolia. Okay. Let's have a look to the GPS now. This is work done, compilation, in collaboration with Enrico Serpelloni, again, ENGV, Bologna. And then this is the velocity respect to Eurasia fix. You may see that two important things. First of all, Africa is moving in this direction with respect to Eurasia. And the velocity of that is on the order of 5.5 centimeters, no more. So it's a pretty slow motion in this direction, okay? Then when you go to see things, what is happening, you realize that immediately that this microplate here, called Adria, is now moving completely opposite to that toward northeast. And then also you realize that there is a plate circuit with Adria that is forming this large-scale toroidal flow around the polar rotation position in the Nile Delta, with acceleration toward north, and then east-west toward the east, and then accelerating again south to the southwestward. So this is forming a circuit from Arabia, Anatolia, and Aegean, accelerating this sense. So you realize that this velocity is far higher than the velocity of convergence, and this means that the plate inside the Mediterranean is moving irrespectively of the overall convergence frame. So it's completely different what you expect to have the Pacific. Okay. So now the question is, what is the driving force of this kind of process? Why this microplate is moving this direction? Why Hadria is moving toward the northeast? And why you have the old circuit if Africa is moving only in this direction? The velocity is much higher. So now what we can do is to try to take all the data that I showed you before, coming from the geological side and also the seismological side, putting together those data to try to see what can be the best model to explain that. Okay. So we can go doing numerical model, we can do analog model. It's a numbers of model that we can do. And it's important to refer to that because this is the only way we have to get a physical understanding of a process. So maybe not simulating the natural system itself, but understanding the process. And the fundamental process in the Mediterranean is such, that is what we are mentioning before, the subduction rollback. So if the velocity of convergence between two plates is very slow, and if you have the subduction of a dense body inside the mantle, then its velocity is scaled with this buoyancy. It tends to go down, but if you decompose the component along the deep of the slab, then you have a residual component that force the trench to retreat, or the subduction to roll back. And so this is actually what happened here, where the velocity of convergence is very low. You have the subduction, and then in step 2 is going trench retreat or slab rollback. So this concept of trench retreat and slab rollback was actually formed in the Mediterranean after John Dewey intuition by Malinverno Ryan in '86, and is exactly the concept fundamental for the process here, and was elaborated further on, and then explaining the formation of the arc. Like in this area, there was the ocean. The ocean is more easy to subduct, and so you form an arc that is following this corridor and trying to consume all the things. And so to do that, you will form an arc, and then your slab can roll back. And this being estimated also by gravity anomaly. And then in this concept of Wikiroiden, you can see that this form, because the Mediterranean is still in an incomplete phase of collision, so slowly approaching one each other. And during this time, this subducting ocean can still do whatever they want. And this process may also be accelerated if you have what we call slab breakoff. So if a part of continental material is trying to subduct by is lighter, then the dense part is detaching from the surface and is forming this, unzipping the slab and propagating the slab. So accelerating the trench. And this was an intuition from the group of Utrecht. And so the result of this process is something like that. You form an arcs because you have trench retreat, in this case of Calabria Trench, that was here, arrived here, more than 800 kilometers of retreat. And during that case, the slab is like that. You open 2 oceanic basins. One first is the Liguro-Provençal, and then everything stopped, and then open the Mediterranean basin. So 3 pulses of spreading, intermittent, not continuous. So why is that? Now you can see again in the reconstruction, there was this seaway with the ocean. The slab is around, going down, backward, and progressively arrive to the present day something. And here we have the velocity of this trench retreat. So what we can do is to take the tomography, because we know the amount of extension, and then we can do an exercise and restore this tomography in time. So this is the velocity, the tomography redrawn. And then what we can do is to take out, restoring back our trench, take out pieces of our slab, and we arrive to 35 million years. At that time, we already have a small subduction that is start navigating to the mountain. So we mentioned before that there was 2 phases of subduction. One, the first opening this episode, then with the rotation of Sardinia Corsica, and then 5 million years of stop, and then restart again. So when you look at this diagram, even if very simplified, you realize that this was happening because at that time, maybe the slab was touching the 660 discontinuity again, which is the discontinuity that is kind of impermeable on this time scale, and then the slab then fall back and go down this direction. So that's interesting. We can test this model, and this is a very simple test that we done in one of the laboratory at that time. So we put some syrup, glucose syrup, different viscosity, more enriched for simulating the lower mantle, more lighter for the upper mantle, and on top of that, a silicon slab is denser than that. Without pushing, we just put a little piece of slab into the mantle to mimic the situation at 35, and the slab was going in this direction, encounter the more viscous part, not penetrating, but stalling for some million years, turning, which are hours in the lab, obviously, in scale, turning, that folding, and then approaching this situation. So with a very simple experiment on density driven, we can mimic probably what happened on a very big scale in the Mediterranean. But then we slowly realized, at the time we were super happy because, you know, at the time, it was 20 years ago, no numerical model was able to do sophisticated things, or very few of them. And so we were almost the first one to really understand what happened. And then we realized that the stopping phase for 5 million years was really the timing when you switch from a poloidal kind of motion of material. So the rollback, to have the rollback, you have to move material from the back of the slab to let the slab retreat to the front of the slab. And if you open this channel here, then you can really move material freely. But when you seal it, because the slab arrived to the end, then you have no other way to do that than turning the material around the edge of the slab. And this is what we learned. So now the things is getting more complicated. And then this is, for example, okay, no, not this one, okay. This one. Okay, so you have this motion of material. Back on the laser pointer. This is the poloidal flow accompanying by tracking the particle into the siren. And this is what happened on the surface. This is the trench, and you have a large-scale motion of material, toroidal one, at the edge of the slab. So only if you have space on the side, your slab can retreat. Otherwise, it has to stop at a certain moment. So we were understanding that not only model in the tank, but also numerical model. And so this was something that opened clearly our mind. The process of subduction is 3D. If you have the slab right to the 660 to let him continuing rolling back, then you have to move material from the below the slab, where it's overpressure, to the upper part. And this is happening if you have some space laterally. Otherwise, will not happen. Coming back to the case of the Mediterranean, now looking back at the arcs of the Calabria, so very narrow arcs. So why this arc is forming then? The arc is forming because you open big slab window on the side. One is on the Sicily channel, and the other one is the southern Apennine. And so we can imagine that once upon a time the slab was continuous, but then when I arrived to the bottom, to continue in this story, you have to open window, and then it broke apart here, where the tomography show low velocity anomaly, with a big slab window on one side, and then another slab window. Only when you do that, then your slab is getting narrower, and now it's free to move laterally and backward, and then to produce this narrow arc. So there is a dynamic, thermodynamic explanation for the formation of the arcs. And this was even better shown by Valentina Magni, one of our PhD, that was simulating that process in numerical. So here you have an oblique view of a tank where we put a slab. The section of the slab you will see here is the central section. And this is the upper view of our model at the beginning. So we have two pieces of continent, and the blue is the ocean. The pieces of continent will go, and the subduction of the ocean is here, the trench is here, and this little slab is still oceanic. So let's see what happened. The model starts, subduction, now stop. And then the two blocks arrive to subduction zone. Oops, sorry. Two blocks arrive in subduction zone. The slab arrive to the bottom, you start folding back. The continent arrive, it starts subducting, but they are more light. and then the trenches start retreating, forming the arc, but then everything stops, and then you have a break in the slab laterally, and so your arc is still, you keep retreating very fastly and forming a very narrow arc, and the side you have a slab window, and you end up with a very narrow slab. And so this is physically what happened. Again, I'll show you again the movie. I think it's pretty interesting to see that. Slab is going down, the section, this is the trench retreat velocity. The first episode of extension here, then everything is blocked because continent is arriving. It doesn't want the first arcwater of the slab, but to have the real arc, and you have to wait for the slab to broken, this white dot laterally, and then you form a very narrow arc that is retreating very fast with an opening of Beckard Basin, an oceanic basin. So in drawing, you start from a situation like that. We are now seeing the slab from the front, the continental block arriving. It's arriving at trans, but doesn't want subduct because it's too light, it's break off, but then it's unzipping the break off. Then you have toroidal flow that starts laterally flowing, consuming the slab, and then the trench is getting narrower and narrower until it broke off. And then you get into a stage that is nearby the one in Calabria. The toroidal flow is here, you can have mountain here, Mount Etna, for example, and then you end up with a very, very small slab. You end up with a slab in 10 million years, you get rid of all the slab, and then before was 1,500 kilometers long, and then in a few million years, your slab is almost finished in a situation that, like the one we have in the Carpathia. Now the question is, okay, that's all fine. We start understanding the mechanism, but do we have the possibility to really simulate what's now happening in the mantle below the Mediterranean? Well, for that, I knock on the door, another colleague, Thorsten Becker from UT Austin, where we try to develop together a methodology to simulate really the mantle behind the mantle pattern behind the Mediterranean. And so is a global model of convection with very high resolution in the Mediterranean, where the tomographic data are good enough to provide us the detail of what happened. And so this method is just taking the tomography anomaly, converting that into temperature, then density, and then the mantle start convect and instantaneously provide a pattern of deformation on the surface. So the conversion, this model is starting from very simple assumption, if you like, but then we go with so incompressible fluid laminar flow and using Newtonian, but also non-Newtonian material, and then and the scaling is obviously simplified because we assume only temperature scaling and not density scaling aside the continental keel that we don't have it in Mediterranean or other chemical anomaly. But the good thing is that we can compare the result of our model directly with the GPS for the surface deformation, for dynamic topography, and the mantle anisotropy. So let's give a look at what happened. Conversion of tomography of Claudio Piromallo inside the slab. We let Africa converge. This is we impose the convergence of Africa to Eurasia, and then we let the microplate, Anatolia, Aegean, and Adria free to do whatever they want. Those are the slab drawn, and then what we observe as a result of the model only by the convection is that Adria is not going along with Africa, but separate and move in another direction. The orange is the GPS. So is turning in the right direction following the GPS, with respect to Eurasia reference frame. We also observed that the motion of Anatolia is pretty good in terms of comparable to the GPS, but the Aegean, for example, not at all. So it's not accelerated in the sense. But what is very interesting is that we can make a cross section along in our model, and then these walls come out. Behind you have the tomography, and the arrow is the result of the convection process. So what I think is important to realize here, that we were able at the time to capture a very small scale convection cell that go from the bottom of the lithosphere to 300, 400 kilometers, so very small convection cell. And so what you have is that you have material upwelling in nearby the near Middle East, flowing below Anatolia, maybe dragging Anatolia westward. Then the mantle flow go against the retreating Hellenic slab, so pointing out in this direction. Then it's going up and going down again because it's squeezed between the two subduction zones. And then it's going up again in the Massif Central. So you have a really small scale convection. And to better appreciate, you can look at these images. Well, you have the horizontal is the velocity at 200 kilometers, but the red and the blue are the material going up and down. And so you really have potatoes of material going down below the subduction zone and material going up. And then when you go at 400 kilometers, these things is getting more less clear. And then when you go at 600 kilometers, everything vanished. So it's really an upper mantle kind of stuff. Yes, Ron.
Quick question. Do you think that the IIFR plume has any effect on the...
Yes, very good question. I've been working on that. I don't have material with me today, but I can tell you that I've been working on that. And if you're interested, I can send you one of our results of paper where we enlarged this reconstruction also to our Africa. And we think that what is arriving here is exactly the African plume. And we think that the IIFR plume. And we think that the motion of Anatolia is due to that. So this creation of this toroidal flow here is exactly like that. Very good point. We have evidence of that on the fact that we have very high, very low velocity anomaly below Anatolia, but also below the Middle East, Arabia. And we have a progression in volcanism from afar to Arabia. And where the flow is like a finger moving to the east of the Red Sea and then flowing upward to inside the Mediterranean. So we think that actually the IIFR plume material arrived below Turkey around 10 million years ago or so. And this is what is driving is westward motion. So very good question. I can send you a paper on that. We published in 2012.
Yeah, please. Okay, thank you very much.
You're welcome. Right. So the test is interesting, this method. Why this method is interesting? Because we then do a numbers of tests. We can say, for example, let's now we put Alps, not for example, let's see what is the role of the Alps. And then you can see that when you take out the alpine collision, then the motion is going in the right direction for Adria. But if you put the Alps as active subduction, then the motion of Adria is completely different. So you can do a numbers of tests. For example, you can test also the role of the motion of Africa. You stop Africa, and you can see that Anatolia is still moving, just because it's a convection that is moving Anatolia, which is moving actually faster than the northward motion of Arabia. So it's not an escape as a result of an alpine of an Arabian collision, but it's a drag due to this large-scale toroidal flow, as we will discuss. And also, you can see that Adria also is moving. So you can do a numbers of tests. So this is for horizontal, but you can also check the vertical motion. So here we introduce a concept I hope you are familiar with, but I can go through quickly, of the dynamic topography. So topography that we see on the Earth is the result of two components, a dynamic and isostatic component. So isostatic is classically due to the buoyancy of the lithosphere, so density and thickness. But for the dynamic component is the stress due to mantle convection at the base of the lithosphere that produce uplift or subsidence. Okay, so if there's mantle convection, we expect to have some dynamic topography component in the terrain. Let's have a look. One thing that we could do is to estimate actually the residual topography, which is this kind of picture here. So in red is positive, in blue is negative, it's hundreds of meters, it's 1 kilometer, 2 kilometers. So what is the residual topography? It's nothing less than we take our model of crust, as we know, in the Mediterranean, it's pretty well known. You filter the component from the topography, the actual topography, you take out what is expected as a contribution from isostasy, and what is left over is the residual topography. So you can estimate that. You can see that there's quite a lot of residual topography everywhere. You can see that there is no real isostatic, it's not zero. There's always a negative here or positive component, which is remarkable. And is, for example, if you go in the Atlas here, where we know that probably is the trace of a Canary hotspot coming, there's a very large residual topography. And you can also estimate then inverting the free air gravity anomaly in somehow, and you can see that the result is similar, also taking independently data set. So there is a match with that. And also what you can do is to compare the residual topography, what we calculate from our model. And you can see that there are things that correspond. For example, you have an anomaly here in the Western Mediterranean, which is similar to what we have from the residual. So dynamic topography is just calculated by mantle convection here, so it's a model. Then you have the high velocity anomaly here, high velocity anomaly here. So what this means, this negative residual means that the topography is here is deeper than what it should be. Okay, there is a component of subduction that depress the topography. Right? When positive is that is the topography is larger than it should be. Without that, the topography should be lower. Right? So, and also on the east. And then we can go in the field and recognize that. For example, this with positive topography in Spain is really what you observe when you go in Spain. If you fly to Madrid, you landed at an airport. It's not at zero. Is everything is on 600, 1 kilometer elevation, kilometer and a half, for example, here in the Iberian chain, no tectonics, and very small tectonics, but positive motion. And also Anatolia, we think is due to this deep convection in the mantle. But also there is an area like Massif Central in France, where you can really measure, like Valérie have done, the amount of uplift in time, having a residual of 500 meters with an uplift of 250 meters on land 2 million years. The Iberian chain is Valentina work, for example, was on more than 500 meters on average from the middle Pleistocene. So you can go in the field and see what happened using geological arguments and try to give an estimate of the velocity, for example, of motion upward and downward. Another area which is very interesting is the Apennine. So here you can have a cross-section along the Apennine where you can see the topography in black and the crustal thickness in yellow. And you see the topography of the Apennine go up to 1 kilometer, 600 meters on average. But you can see that where the topography is higher, the crustal thickness is lower. So it go against what we expect to have from this isostasy. And this is probably due to the fact that there's a dynamic component. So we calculate the residual, we calculate the mantle flow, and then if you put the tomography on top, you realize that in the central part where we have this residual of more than 500 meters, you also have no high velocity anomaly. So probably there is a gap in the slab. So whereas the negative side in the northern Apennine and Calabria, the subduction is active, and so it's pulling down over 500 meters. So on top of a subduction zone, there is a negative residual topography around 500 meters. So all in all, we found that we can go in the field and measuring the amount of uplift and what happened, I mean, in terms of residual topography. So almost no region in the Mediterranean is in isostasy. The other test is the third test. You can go with and compare with the tomography, and so you can see whether the anisotropy match the mantle flow, and blue is happy, red is not, and you can see that we are able to match with our mantle flow a lot of signal, for example, in the Western Mediterranean and partly also in the East. And this, so this back-arc flow can go a pretty good fit as a return flow to the subduction zone, attracting material of a large scale. The last test is really the volcanism. So here I plot the orogenic volcanism due to subduction, and orogenic one is green. And you can see that the anorogenic one is on the low velocity anomaly, whereas the orogenic is on the high velocity anomaly. So the volcanism match fairly well the tomography at that. Okay, now trying to summing up what happened. What is the mantle flow pattern then? I think what we can see is that we have a large-scale return flow of the two subduction zones. One was the Western, and now another one in the Eastern Mediterranean. And so this subduction zone is attracting material in this way, and it is matching pretty well the anisotropy in the Western material, in the Eastern Mediterranean, and on the other one, including the contribution of Arabia, then you have material that is flowing in this direction toward the Eastern subduction, Atlantic subduction zone. But also, if you put the volcanism, you can see that there is material that is upwelling as a return flow of this large scale in several places around the Mediterranean, match fairly well the low velocity anomaly and the dynamic topography areas that where you go down there. So two large scale convection. So you can really have a situation, similar pattern like that. Two subduction zone falling down into the mantle, convergence of Africa very slow. This produces a large scale return flow. One is here, and very lot of small scale one around the slab. And this may match the first order indication in terms of mantle pattern convection, but also the geological signal on the surface in terms of topography and tectonics. So, running to my conclusion, I hope I can convince you that the subduction slab pool dominated system is localized in the Mediterranean. You have to imagine like you've been in a tank with a fish tank, where you let flowing material by density that is going down into the mantle and produce this return flow at every scale. And so is a system that is almost protected from the large-scale convection. The flow, this kind of flow we're talking about is restricted into the upper mantle and is very confined, very small-scale convection, and so produce a very strong vertical deformation just because it's very shallow, and so have a very greatest pressure on the surface in terms of tectonics. And then we have a large-scale return flow beneath Anatolia, southern France, and Iberia, and small-scale toroidal flow at the edge. The open question is how much the entrance of material from Arabia, sketched like that, may really, from Africa, afar plume, may have influenced, for example, the subduction in the Aegean. That is an open question. We need, by the way, a better model definition of crustal deformation and dynamic topography on the field. So more field work, but also more refined regional model like that, where we can incorporate, for example, crust and potential energy that better explain the sum of the pattern we see on the surface. And with that, I thank you very much for your attention. I'm happy to take your question. And then if you want to ask me more questions, just have to write me an email, and I'm going to be happy to answer to all your questions, send you material. You can find some of the paper we are referring to here in this list. Thanks a lot.
Thank you very much, Claudio. It was very interesting. And also you connected with the East African Rift.
This is actually, I've been working very much on the East African Rift, on the Arabia breakup, and on the mantle. So all my last year, you asked me to talk about the Mediterranean. Next time, if you like, I can talk about the Ethiopian NFR. We'll be working a lot in Ethiopia, and also on the mantle flow between mantle convection between the FR and the Northern Arabia collision also. So I would be happy to share with you all my findings.
Okay, thank you very much. So anyone can ask a question, put it in the chat, I can read it for you, or raise your hands and I'll give you the floor. Any question?
A lot of material to digest.
Yes, yes. Okay, so maybe I'll ask one. Usually I leave the floor to all the participants, but if no one wants to say something, I don't know why, but I thought I had, I had read that there was this, Etna could have been a mantle plume actually. And initially the geochemical signature of Etna was related to OIB. And with time, the geochemical signature of Etna changed more to products produced by subduction. So do you have any comment?
Yes, actually, we've been working on that quite a lot. We're thinking that, along on the edge of return on the end. Now, I don't have the slides that exactly on that, but I have another file that will take too much time to open. But to answer quickly, the toroidal flow that you create along the edge of the Calabrian slab has a vertical component because the slab is oblique.
Yeah.
So our thinking is that Etna is a mixture of composition between something related to this toroidal flow in the mantle that has been anyway a little bit contaminated also by the slab. So it's not really a plume in the sense of a hotspot, but it's a plume induced by the subduction of the Calabrian slab. It's not an arc volcanism either. It's just on the side of the subduction zone. And we think one solution may be that is driven by that process. We have done some numerical model, and then we see that there is the toroidal flow may well explain not only this trace of the volcans that is centered exactly where it should be, but also this pattern of anisotropy. It's pretty clear. So, yeah.
Yeah, but the OIB signature is usually a deep signature. So you think that.
Yeah, the geochemical signature of Etna is a mixture kind of. It's not subduction related.
Yeah.
But it's not plume related either. I mean, so that's what I learned. And then, a good explanation for that could be that is related to mantle convection, not related, induced by the subduction, but not related to the melting of and rising of in the volcanic arc setting. And this is probably similar to what happened to the Massif Central, for example, in France, or many other intraplate volcanism that are along the edge of the high velocity zone in the Mediterranean. Yeah. So if I take again, maybe I can go again to that slides where I can showing the position of them. Right. Yeah, all right. Yeah, for example, the Massif Central you can see is here.
Yeah.
But there is also the Eiffel here, the other volcans here. This is all intraplate volcanism. And also here, and also all here. The very reason is not related to plume, is not related to slab, it's related to mantle convection, we think, due to this convection in the mantle related to the subduction. But it's not on the position of the volcanic arc and doesn't have any signature about it. So and apart from this one, that we thought is probably related to the ICTP plume.
Okay. Okay. Thank you. I have a question by René Wild. Please.
Yeah. Hello, good afternoon. Can you hear me?
Sure.
Yes.
Very well.
Oh, yeah. Thank you for this very nice talk. I have a question regarding this very same picture that you suggested that this could be associated with the ICTP plume, and that this somehow could explain part of the eastward component of on GPS velocities we see today. However, I kind of challenge this interpretation, because if this was the case, then in the Red Sea, Saudi Arabia, where the plume is right below it, we should see some of the effect of that. However, from what we see in GPS and internal deformation with the Arabian Plate and the motion of the Red Sea, it is likely that the driving force is actually the collision between Arabia and Eurasia. So, how it comes that you suggest this interpretation for the north, but in the south, if this was true, which will have an effect which is larger, we don't actually see it.
All right, that's a very good question, and maybe I can open another file. I don't know if I have the time, and if you, but it's a very good point where we've been working on for quite a lot on the last years. And okay, so the question is the driving force of Arabia. Is that correct? Now,
yes, yeah,
perfect. Okay, so it's a very important question, so it's not super easy to answer. Let me check. We have done some work to try to understand that, and maybe I can show you something here. Okay. Okay, share my screen again. Here. Okay. Here. Now, there are the problem when let me see. Let me take a reconstruction. Let's start from this. Okay. Okay. Let me start from the first question is that, I mean, when you look at the motion, okay, the motion of Arabia, you're right, is this direction, okay, nowadays, and has been constant in the last the last million years, almost always constant, about 3 centimeters per year. So this is the northward velocity of Arabia in time. Before was attached to Africa, then it's detached around 30, and it keeps going at the same rate, okay, of Arabia. Okay. This is what we know. So during the opening of this sea, and also what we know is that around 30 million years, when you start opening the Red Sea and the Gulf of Aden, you do have a kind of subduction here, but here we already have the consumption of continental industry. Okay. Therefore, the pattern of motion of Arabia, now when you look at that in the simple words, you have the opening of, and then also at that time you have the placement of the ICTP plume with Ethiopian large Indus province and the plateau, Ethiopian plateau, and very large uplift of all Yemen up to Sinai, up to Jordan, so an enormous upwelling. So this is known and well established. So it's enormous things. So we have a large upwelling on the back and a collision on the front. The collision keep going at 2023. There is probably no slab anymore here, or start almost broken. And then you start keep opening and keep the Africa at the same rate. So it is difficult for me to imagine that subduction may drive this process, is actually at the time you need to have a low slab pool. So when you open the Red Sea, for example, Gulf of Aden, in this area, you really have break off the slab. So the slab pool forces was very low. The only region that keep subduction active is Macron, but it's very small.
That's right.
All these things. So now it's interesting to look at, for example, tomography to answer this question. So now give a look to the tomography. Today, what you have is a large downwelling here, a high velocity anomaly here, and a high velocity anomaly in the GEON, and there's an enormous positive anomaly here in FR. So all the model, you have 3 models, they all agree on that. But you can also see that if you do a cross section here from the FR to the Turkey, you see this is south, you have the FR plume, and then you have a very large long tongue of low velocity anomaly that go here. And here you have the trace of the broken slab of the Tethyan slab in all the model. Okay, so you see that. Now, if you put on top of that the volcanism, which is something that is here, for example, here's the volcanism. You see that volcanism started here 35 million years ago. He arrived to Arabia around 25 million years ago. He arrived here 24 million years ago. He arrived here 10 million years ago. So there is a progression in volcanism. So one possibility is that you really have, and then you have a large residual topography on top of the tomography. So FR plume looks continuously going toward the east shoulder, west shoulder of Arabia on the Red Sea, which is very much elevated, and then keep going up to at least Jordan, where you still have volcanism, Arat Sham, LIP volcanism, and also topography. So, in our opinion, it's this large-scale return flow that is dragging Arabia northward. The downgoing plate of the Tethyan slab and upwelling of the FR. This is a circuit, we call it the conveyor belt, that may drive Arabia to the north. And this is the way to explain the process, because in this way, we can explain the fact that Arabia is keep going toward the north at the same rate, irrespective of the fact that you are building up an enormous collisional belt. And you should expect to have a decrease in velocity. So that's our opinion. Maybe wrong. We've done some model. I don't have time to show. But we also think this has a large number of consequences, like the Nile Delta, immigration of plenty of other effects that we've been working on the last year in terms of dynamic development. So
I see. Thank you very much. Sorry, it wasn't my intention to divert from the main subject, but
no,
it's the really good points you have made.
Very happy to keep the conversation. Just drop me an email and we can keep going.
I will definitely. Yes.
Okay. You have to unmute, I think.
Yeah, because there was noise around, so I try to not disturb you. I said that there was a raised hand, Puspendu Saha, but at the same time, I have 2 persons in the chat who posted before, so I'll go first with the chat. So the first question is from Betty Higgs. Thank you, Claudio. Very interesting. For your FE models, what is the modeling resolution?
That's a modeling question for the Mediterranean model. Okay. We can go. Allora, there is a challenging model because it's a global model, and with zooming into that high resolution into the Mediterranean. Now, it would have been the resolution in the Mediterranean is also related to the resolution of the tomography. So we can go even further at high resolution, but if the tomography cell is still in the order of 50 or 100 kilometers, doesn't make a lot of sense to go further on, because we thought the Mediterranean was good enough in terms of resolution, and we done also this exercise in the Western US because the resolution is good there for tomography, and therefore, when you have the high resolution of tomography down to 50 kilometers, for example, cell, then you can capture the small scale convection. We cannot capture that if the resolution of the tomography is higher, which is that global model actually do. So it's really depending on the number of stations you have. And so you adapt to that the numerical model, where, for example, just to give an idea, the plate boundary is on the order of some tens of kilometers large. So it's not, it's pretty large area, like 40, 30 kilometers, something like that, where we put low viscosity zone. So it's very simplified. The model has a lithosphere that is only higher viscosity, but has no crust and has no potential energy actually in the system. So there is potential energy, but there is no crustal material. So you don't have really the deformation on the surface. And so all is viscous. So there is a long way to go to get something more realistic. And then, especially if you want to have, compared with GPS, you need to have the faults, localized deformation, putting the deformation inside the convection system. This is the real challenge. Some people is trying to do, but this is still a global model. And then this is the real challenge, I think, for the future for you guys that are growing this. I mean, I'm done, but maybe in the future we can do that. It really requires a lot of work. And this is the next challenge, I hope.
Yeah. Okay. The next question is from Yiduo Liu. Thank you for the fantastic talk, Professor Faccenna. My question is the rapid motion of Anatolia driven predominantly by Mantle flow via basal traction?
Yes, I think so. I think so, yeah. And we test that, actually. One of the models just showing that. No convergence, Arabia stop, Africa stop, still moving at the rate that is comparable to what we have. And this is explaining why, if you look at the Eastern Turkish earthquake, for example, it's really only slightly. There's no compression there because the Anatolia is moving to a faster rate than Arabia go north. And so it's not pushed on the side, but it's dragged. And from the Hellenic trench and from this from the return flow of the Hellenic trench, but also coupled with the IIFR plume. That's what we think. And I think in this conclusion also, many other authors are going that direction in the recent years.
Okay. Thank you. Now, Puspandu Saha, you raise your hand, you can speak.
Hello, Professor. So thank you very much for a nice talk. I have a very small question on the formation of two back arc basins, what you mentioned. In case of for formation of two back arc basins, so why don't you think that it is easier to reactivate or opening of the earlier back arc basin than the formation of a new back arc basin? Because to form a new back arc basin, you need to break the continental crust. So you already have a back arc basin in the system. So why don't you think that it is easier to opening up further the earlier basin? So how do you comment on that? Because in analog experiments, it is very difficult to develop two back arc basins simultaneously in a model. So what do you think on this?
It's a very good point. I mean, so if I understand correctly, Puspandu, is that the question is why extension that was in the Liguro-Provençal basin in the Mediterranean then start opening a new one? Why still keep not in that one? Yeah. I don't know. No, I mean, I have some ideas, but it's a very good question. This is a question is why we don't keep opening the basin that is already open, and also oceanic floor there, and then we move the material there. One possibility is really, let me see if I can open again the previous, I think it's still there. Okay, if you look at the reconstruction, okay, let's look to the reconstruction quite. That one possibility, I'm not sure, but one possibility, 20 million years, you open the first backcrack basin, okay?
Yeah.
So, okay, you open this one.
Yeah.
Okay, then you start the rotation of the back, and then you form this eye angle. Now, when you are reaching this stage, the curvature of the slab is very strong. I mean, you cannot do much. And here there is Africa, and Africa is a very strong continent. We know it doesn't want to abduct. So at a certain moment here, you are really in a position of a collisional zone. 50 million years, everything stopped. Then at 10 million years, you have the break off of the slab here. Now, this slab is completely disconnected from this side, and the tip of the slab is somewhere here near Tunisia. So the next step was opening of the Becker system just here. So I think there is an issue respect to the fact that all this block was somehow now disconnected from the system. And so the next slab Becker basin is here. And this is probably due to the toroidal flow, I think. So when you basically at this moment everything stopped because no toroidal flow, no slab window. You form a slab window, you start circulating material, and then you restart retreat, and the toroidal flow probably influencing the opening of this new basin, which is actually very small, and also reactivating an area that was compressed before, so it was not really strong, and this was collapsing down. So probably it's due to this geometrical configuration.
Okay.
What we learn is that opening a Becker basin requires a collision on the side. This is also the model. If you have collision on the side, you open Becker basin. You never open a Becker basin only by trenching it. You have to collide somehow, and then you retreat on the other side. This is what we learn. And naturally, it's only like that, even in the Western Pacific.
Okay. Thank you, Prof.
Welcome.
Professor.
Okay, any more questions? Betty Higgs in the chat say, thank you, Claudio.
Yeah, you're welcome. I'm very pleased to be with you. And then anything, please drop me a note on email. You can find my email everywhere. And I would be very pleased to answer you and to discuss with you. And if you want to know more about the Nile River and Afar, Plume Afar, I will be happy to join you again.
Okay. Well, we'll thank you very much. I mean, the ICTP-EAIFR, thank you very much for your accepting to give us a talk in our geophysics. And also, I thank also all the participants who joined us tonight. And yeah, I think I'll stop the recording and we'll